Okay, in terms of reviewing questions 14, 15, and 16 um, on the final exam part 1 review, we have free radical halogenation, and the question is, what are the major products given these particular sets of conditions? Now remember that when we're doing this, we first of all need to know our selectivities. And in this case, our selectivities are that the primary to secondary to tertiary position ratios for primaries are always 1. And then for bromination, it is 80 to 1700. That's for bromination at room temperature. And for chlorination at room temperature, it's 1 to 3.4 to 5 would be chlorination at room temperature. So that means that those selectivities we're going to use to balance out the statistics of the reaction. So the first thing we have to do is go through this molecule and figure out how many unique products we have. Well, I can tell you down here we have 4 unique products, but where did they come from? They came from replacing a primary hydrogen, let's say on carbon A, and A, or replacing a secondary hydrogen, substituting a secondary hydrogen of B, and there's a B, and there's a third B, replacing a tertiary hydrogen on position C, which there are 3 of those, and then replacing one of the 2 hydrogens on position D. So this is where products A, B, C, and D come from. So let's take them one at a time. For looking at basically the percentage of A, remember we take the number of hydrogens and multiply it by the selectivity for that position, and in this case with bromination. So for A, there are 3 hydrogens on each one of those methyl groups. There are 1, 2, 3 hydrogens, which means there's 9 times a selectivity of 1. For B, there is 2 times 3, which means there are 6 hydrogens times a selectivity of 3.4. For position C, there is 1 hydrogen, and there are 3 of those at a selectivity of 5. And then finally for product D, there's 2 hydrogens, 3 positions, D, 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 those 3 positions, so there's 6 hydrogens, and because those are secondary hydrogens, they get I'm not going to go back and erase this. That was for chlorination, which will be down here in the next problem. Sorry, for position A, it's 1, 80, 1700, and 80 for bromination at room temperature. So we've got a grand total of 9 for A, 180, or 480 for B, 5100 for C, and 480 for D, and so clearly the major product in this case is C. And that's always going to be the case for bromination at room temperature, because the selectivity of the tertiary position is 1700 to 1. It will always be that you'll brominate the tertiary position first before you brominate any secondary positions. Now, coming down here, we have the same type of analysis. We've got A's and B's and C's, and then position D. Sorry, that's a D. That's a B. D. So we've got A, B, C, and D using the same numbers as what we just did up here. We've got 9 for A, we've got 9 A's times a selectivity of 1 for chlorination. For B, we've got 6 hydrogens times 3.4. For C, we've got 3 hydrogens times a selectivity of 5. And then for D, we've got 6 more hydrogens because there's 2 per position D, times a selectivity of 3.4, which means B and D, which is letter E, in what I've given you is the correct answer, because B and D would be formed in equal amounts. So again, what I'm doing is I'm taking the number of hydrogens and multiplying it by the selectivity of what kind of hydrogen that is, whether it's primary, secondary, or tertiary. So then it says, what's the major product of the reaction below at greater than 300 degrees Celsius? So if we go back up to our selectivities, the selectivities become 1 to 1 to 1 at greater than 300 degrees Celsius for any halogenation. And so in this case, we've got, again, 9 hydrogens for A positions, 3 times CH3s. For B's, we've got 3 times 2, so we've got 6 hydrogens for B. For C, we've got 1, 2, 3 hydrogens. And for D, we've got 2, 4, 6. So we've got 6 hydrogens for D. All of those are multiplied by 1, so this is pure statistics. And so we've got a 9, a 6, a 3, and a 6, which means in this case A is the major product of that reaction. So that is how we would do free radical halogenation. So again, the formula is number of hydrogens times the selectivities. You would get the selectivities on an exam. I would always give you those, but they vary from bromination, chlorination, and then when you're at greater than 300 degrees Celsius, they're all the same. Now, if we look at problems 29 through 33, it's a similar problem, only I'm looking at it from what reagent should I use to give me the highest percent yield. So again, looking at this, the selectivity of bromination at room temperature is 1700 to 80 to 1. That's tertiary position to secondary position to primary position. Chlorination at room temperature is going to be 5 to 3.4 to 1, and then either bromination or chlorination at room temperature is going to be 1 to 1 to 1, because it's totally based on statistics. So in the first reaction, what I'd like to do is I'd like to put the halogen at a secondary position. What reaction is going to give me the highest percent yield? Well, looking at this, I've got A, B, C, and then B and A, because A and B give the same product. So I've got 6 A's, I've got 4 B's, and I've got 2 C's. So if I want to put the halogen, if I want to substitute for a secondary hydrogen at position B, I need the most selective reagent, which means in this case I would like to do bromination at room temperature, because that'll give me 6 times 1 for the primary position. Each of these other 2 is secondary, so it's going to be times 80 times 80, and so that will give me the highest percentage of those products. If you went chlorination here, you would have a 1, a 3.4, and a 3.4, and in this case what you would end up with is, here you end up with a 1, a 320, and a 160. So I'm looking at the percentage of 320 out of the total sum here, which is 481. So for bromination at room temperature, it's 481 out of, or sorry, it's 481. It's going to be 320 out of 481 would be my first would be my overall percentage. And if I do chlorination, it's going to be a 6, a 13.6, and then a 2 times 3.4, which is 6.8. In this case, I would get 13.6 out of 12, 15, let's see, 12, 25, 26.4. Here you can see it's only 50%, whereas over here it's definitely greater than 50%. So bromination A would be my first, would be the best way, would be the way to make that product in the highest percent yield. And so that's how we would approach every one of these problems. If I look at the second problem, I'm wanting to brominate, I'm wanting to halogenate at the primary position. And the only way I'm going to get the highest percent yield at the primary position over the secondaries, because again, we've got a secondary, we've got another secondary, a third secondary, and another primary. So again, this was A, B, C, B, and A. If I want to have the highest percent yield or highest percentage of halogen at the primary position, I need to use greater than 300 degrees Celsius for this reaction, because I want the reaction to go totally based on statistics. And so again, A, 6 hydrogens, B, 4 hydrogens, C, 2 hydrogens. So I want to favor the statistical group because I want to put that halogen at A, at the A position. So in order to do that, I can use chlorination or bromination at greater than 300 degrees Celsius, which would be C. So that would give me the highest percentage there. So again, I'm kind of thinking backwards here. In this 31, I want to put the halogen at the tertiary position. Whenever I want to do that, I want the most selective reagent. So in this case, I'm going to do this with bromination at room temperature, because I want to put the halogen in the most selective position. And so I want the 1700, I want the 1700 to 80 to 1 set of reagents, tertiary, secondary, primary. So I want to have the selective position here of the tertiary, so that would be bromination at room temperature. For 32, what I have is I'm putting, if I look at this, I've got a CH3 group here, which I would call A, a CH group here, which I'll call B, and then 2 hydrogens here, which I will call C, but they are the same, that's the same position as over here. And then these 2 hydrogens here would be D, and these 2 hydrogens here would also be D. So in this case, I want to put the halogen on the CH2 group, and in this case, the highest percent yield there would be either using bromination, which would probably, well, let's just talk about that, bromination or chlorination at room temperature. Now the problem is bromination in this case, B, I would have a 1 hydrogen, or sorry, for C, which is what I want C, and so at C we would have 1, 2, 3, 4 hydrogens times 80, but position B would have 1 hydrogen at 1700, and so C would not be the major product of that reaction if I do bromination at room temperature. So instead, what I want is a mix of statistics and selectivity. If we look at the difference between B and C here, for chlorination, bromination is going to be 1 hydrogen times 5, or chlorination is going to be 1 hydrogen times 5, 4 hydrogens of C times 3.4, and so that would give a higher percentage. Now note that C and D are going to give the same percentage regardless of what you do, because it's the same number of hydrogens. So when I asked for this one, I could have asked for having the hydrogen, or putting the halogen in that position as well. So in this case, it is going to be chlorination. Now you might say, what about A? So if you look at A for bromination, it's going to be a 3 hydrogens times 1, which isn't much. And down here with chlorination, it's 3 hydrogens times 1, which does not beat number C. So in this case, I would like to use chlorination at room temperature. That will make this as my major product. And then finally, coming down here to the last problem in this set, I would like to replace one of the CH3s with a halogen. And so again, this is A, this is B, C, C, D, and D in terms of my products. Product A is going to have 3 hydrogens. Product B is going to have 1 hydrogen. Product C is going to come from 4 different hydrogens, and D is going to come from another 4 hydrogens. Is there a way to make A the largest number in a reaction? And remember, since A is a primary hydrogen, it's always going to be multiplied by 1. The best case scenario would be to use greater than 300 degrees Celsius for this, so that everything has a selectivity of 1. But even then, A is not going to be the major product, because even if I go full-blown statistics, C and D have it beat. So for reaction 33, the answer is none of these. It's H, which is none of those, because in this case, there is no way to make A the major product. Even under statistics, it only has 3 hydrogens versus C and D having 4. So the whole idea of this set of problems was to think kind of backwards in terms of what conditions would I use to make this product as the highest percent yield. Okay, so that's how we would do that's how we would do those two sets of free radical halogenation reactions.